Thank you so much for the nice introduction. Yeah, and for inviting me here today. And I thank you all for joining. So I'm pleased to be here with you, and I'm going to talk, as Hannah rightly said, on the regional scale assessment of the potential for sustainable intensification of different integrated soil fertility management practices in northern Ghana. So I have to say that we really didn't use a sustainable intensification framework to assess the different integrated soil fertility management practices being presented here. This presentation mostly focuses on the assessment of the performance of these different ISFM practices in northern Ghana. On that, I would like to take you through the structure of the presentation. Moving, okay. So I will start with the background, the problem statement, and I will talk about the material and method, the result. Then I will conclude and I will talk on the future direction and call for action. So what is ISFM? ISFM are a bundle of technologies that have been advocated by AGRA in Africa and implemented in Ghana, particularly in northern part of Ghana, by MOFA, which is the Ministry of Agri, and it was implemented by MOFA in collaboration with different partners under different projects. And the idea behind it was to train farmers on how to manage soil fertility in a more intensive way while keeping it environmentally, economically, and socially sustainable. Why is that important? Because ISFM practices can help to boost yield while protecting the soil health. So by combining organic and inorganic fertility treatment with other good management practices, we can improve the nutrient use while reducing the waste and environmental damage. So in Ghana, like in many other countries in West Africa, population is rapidly growing, and this will lead to raising consumption and wealth, which will place an unprecedented pressure on food system. And this pressure is reflected in food security metrics already, where 6.3% of the population remain undernourished and 12 to 19% of the population are affected by acute food insecurity, which is signaling a gap between the supply and the basic human needs. So on top of that, we also see a gap in maize yield. So a gap between the current maize yield, which is only a fraction of its potential, reported to be 6 tons per hectare. And this low or large yield gap is partly due to the low fertilizer use, the weak soil fertility, soil degradation, and also soil erosion. And these large yield gaps are exacerbated by the risky production environment in which maize is grown, which is characterized by a high rainfall variability leading to recurrent drought and flood. And the prevalence of shallow and sandy soil in the region are creating a volatile landscape, which is making sustainable farming and the long-term food security difficult to achieve without significant intervention. So ISFM practices have been reported to be a key pathway for sustainable intensification. However, their performance vary with location and climate condition. And also a little evidence exists on how these practices interact with soil depth, and the future climate variability in northern Ghana. So this study intend to evaluate the effectiveness of different ISFM practices across varying soil type and sowing date. More specifically, we intend to assess the performance of ISFM practices across soil type, soil date, and climate scenarios in order to identify the most suitable combinations. And also, we want to quantify the impact of the 2-degree warming on maize yield at site-specific location in northern Ghana. So this is the location of our study site on top in the map of West Africa, and on my left in the world map. To achieve our goal, we compile different data sets, including the soil data, the climate data, and the crop data. So the soil data was the soil grid data set was used. We selected 23 grid cells evenly distributed in the northern part of Ghana. And then we use two soil depths, a deep soil and a shallower soil. We use the happy data set where we use two different climate scenarios, the current condition and the warmer condition. We used 3 GCMs under each condition and ended up having for each one of the grid cell above 300 ensemble members. So for the variety, we use the maize Obatampa variety, which is reported to be a maize variety that is commonly grown by the smallholder farmers in the region. We use 5 sowing dates based on expert knowledge, and these sowing dates are reported to be the optimum period within the large sowing window in which most of the farmers generally grow maize or sow maize. And we also use 4 fertility components. This includes the control, which was mainly used for comparison purpose. Then the organic fertilizer, here we use manure, the inorganic fertilizer, and the combination of those two. We use some key indicators to evaluate the performance of our different fertility treatment. This includes the yield distribution using the density plots, the yield stability using the coefficient of variation, and the relative percent of yield change. So the process consisted of calibrating and validating the genetic coefficient of Obatampa, our maize variety, inside simplest modeling framework. Then we proceeded with an upscaling and an harmonization of the climate data set in order to match climate and soil data. And finally, we proceeded with the assessment of the different ISFM practices under different climate, soil, and sowing dates using the different indicators listed. So here, as I said earlier, we use density plots to visualize the distribution of crop yield across different fertility treatment and sowing dates. The y-axis represents the yield and the x-axis. On the x-axis, we have the amount of yield, while on the y-axis, we have the relative frequency of yield value. So the height of each one of the curves show the probability, while the width of each curve shows the variability of yield, how stable the yield is under each of the fertility treatment tested across the different sowing dates. So on the left, we see that the control and the organic treatment overlap, while on the right side, we see that the combined treatment and the inorganic treatment overlap. So the organic and control treatment are consistently peaking at around 1 ton per hectare. They have narrower curves, which means that they are low-yielding treatment, but then more reliable. On the other hand, we see that the curve under the combined and inorganic treatment are wider. And that goes from around 2 We have in June 2010, it's a bit less than 2, but let's say from 2 to 4, the yield vary from 2 to 4, and then, but with high variability. So we can say that the highest grain yield is observed under the inorganic fertility treatment, that regardless of the sowing, but also more variability is observed under this treatment. And as we move from the 10th of June to the 20th of July, we see that the organic treatment, the curve representing the organic and the combined fertility treatment are showing bumping curves, like there are two peaks in particularly in late June to late July. And this suggests that as the season progresses, some plots perform exceptionally well, while some others lag slightly behind. And that is what is creating this multiple sub-peak. So we also looked at biomass under the same conditions, and we observed that the highest biomass is obtained under the combined fertility treatment, and that also regardless of the sowing time. We look at the percent change of yield in the 2-degree warming condition relative to the current condition under different fertility treatment for the early sowing and the late sowing on the deep soil and the shallower soil. And we see that the combined fertility treatment results in yield increase under the warmer condition. And then similar patterns is observed under the organic fertility treatment, but mostly with the early sowing. And the inorganic fertility treatment resulted in yield decrease almost everywhere except when sowing is done late on the deep soil. So we also looked at the coefficient of variation, which indicates yield variability across different GCM in order to show how much the climate model disagree or vary under different conditions. So we see that under the deep soil condition, the deep soil on my right side, the coefficients of variation are lower. This suggests that in deep soil, the outcomes are more stable and the different climate models are in closer agreement. And the reverse is observed on the shallower soil, which means that more uncertainty is observed on the shallower soil, which is the box on the left side. And we also see that when we simulate under the combined fertility treatment and also the inorganic fertility treatment, we see lower coefficient of variation, particularly on the deep soil, while the reverse is observed when we are under the control treatment. And also there is a slight disagreement when we simulate under the warmer condition compared to the current scenario. We also looked at maize yield, the percent change in maize yield under the warmer condition compared to the current scenario. And when maize is sown late under the combined fertility treatment, and the results show that the warmer temperature will result in yield increase in the northwest and part of the northeast. It will result in a slight yield decrease in the southern part, while it will not have an impact at all in some part of the study area, including the southern part of the northwest, here in orange, indicated by the orange circle. So in conclusion, we can say that inorganic treatment resulted in higher yield and more variability, ISFM practices in general can enhance productivity regardless of the sowing time. The uncertainty in climate model scenarios increased when we were on the shallow soil and also when no fertility treatment was applied at all. And the 2-degree warming will slightly increase yield in some part of the study area. It will decrease in some other part, and it will not have effect at all in some part. And for future direction, we can expand the ISFM evaluation across climate and soil context and also improve climate projections for the shallow soils. And for key actions, we can scale up ISFM adoption, strengthen soil-specific climate risk assessment, and implement region-specific climate adaptation strategies. On that, I thank you for your attention, and I will be glad to discuss with you on this.